Okay, well, hello, folks. I think I'll go ahead and get us started. Let me open up in prayer and I'll give you a sense of what we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. I pray that the material will be clear, that this class is helping them to get a better understanding of what it will be like in the future for them in their engineering professions. Also, I pray that you would continue to help them in their spiritual formation, Lord, that they are storing away all of the times that they've been able to study scripture and the interesting facts and things that go on from the stories of so many people in scripture and the theological concepts that we can be deriving from that and applying in our day-to-day life. And I also pray that you would give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're going to today continue to go through our main textbook. And so this is going to be the last lecture that talks about post-development. And so we talked about production, where you can be thinking about going from a single article to multiple articles. We then got a chance to be thinking of operation and support with our last lecture. And what I was trying to have us think about there is how what the operation and maintenance in its deployed environment, what that is all about. And I continue to be thinking about our James Webb Space Telescope as a example for us to get a sense of what that is all about. And in addition to that, now we're going to be talking about systems of systems engineers. And this is going to be a relatively short chapter, but I think it will be interesting for us to get a sense of what it means to do engineering at yet even a higher level. And I think there'll be a chart or two that will help explain what we're going to talk about. So this will take me maybe just a handful of minutes or so, and then we'll get into our parametric diagrams and get into some more details on that front. And I wanted to have us share a video that talks about one of the modalities and how it can be utilized. So first we have a couple of things. We have system of systems, we have systems of systems engineering, and then we're going to be reflecting how traditional system engineering compares to system of systems. So systems of systems engineering, or SOSI, is a specialty of systems engineering that focuses on combining multiple systems together. And so maybe you're thinking of an aggregation of highly complex systems to get even a larger aggregation of capability. So maybe you're thinking about GPS is integrated with some other space systems that together formulate an approach for us to navigate and to do things remotely on the moon or something like that. So that gives you an idea. And this is in order to accomplish an objective that a single system cannot achieve on its own. And so maybe each one of these systems were envisioned to do a certain thing, but when you aggregate it together and have some additional engineering that's put in place, it actually can do beyond just what that basic function was all about. So let's explore what is the difference between these two, traditional system engineering and systems of systems. So we have a couple of slides that will show this. And so there are several differences between what we have here, traditional systems engineering and systems of systems, many of which the traditional system engineering focuses on a single system and single managing organizations, and the system of systems has multiple systems and organizations. So let's talk about 5 things. First, we'll talk about scope and then requirements, and then 3 other items here. So first, for scope, a single system has a well-defined scope to encompass the individual system, whereas the system of system scope will be variable, continually adding, modifying, and removing different constituent systems within the scope. Something else comes online, it has to go down for maintenance, there's a block upgrade. And so now you have multiple things that are trying to collaborate, but they have their own system that they're dependent on to make sure that it continues to stay operational. terms of requirements, a single system will have a well-defined formal requirements in accordance to accomplish its objectives that are clearly developed in accordance with the system engineering lifecycle process. So that's for that particular system. Then for system of system requirements will be less formal in the requirements, and we'll talk about four types of systems where this will become a little bit clearer. That relies upon the individual systems to develop their requirements, processes, and manage their capability development process. So there needs to be some collaboration and coordination, and hoping that everybody does their part. Then we have architecture, testing, and acquisition. For architecture, the individual system will have control over its architecture during the development, much like the requirements. For a system of system architectures, the structure is less supported, relying mostly on the interfaces between the systems within the system. So thus, you have to have these standardized interfaces and make sure that, say, you have a regular periods of time. So for the next year, we've contracted that there's going to be this collaboration that's going to work with all of these systems that have to be coming together. For testing, a single system will likely have one resource sponsor and thus have the access to their dedicated test range environments. On the other hand, system of systems may have less defined items such as who is in charge. And so we'll get into the four different examples of where we'll see that, who controls the resources and who can handle the data. And finally, for acquisition, individual systems have an established acquisition process that is followed in order to clearly define the objectives and the desired end product to accomplish the mission. On the other hand, system of systems often do not have a formal acquisition program and process, with the exception of a directed systems of system. And so thus that system of system is operating as a system. And so it has some of the things that we've had a chance to be thinking about so far in our class. So here is a system of system requirements context. And so we have operational capabilities. Those are being folded into what is the mission capability requirements. Then things are pushed out to one of those systems will have specific supplemental operational requirements that this is their piece. And so you can be thinking of whatever concept you'd like to be thinking of. You can think of like a quartet or some type of sports team. Each person has to be doing their part. They overall have a common shared capability that they're doing, but each one then has to be more specific, more surgical. And so this is the domain of the systems of systems engineer. Up here is what is the mission objective of this overall capability. That's the thing that they're getting a chance to be focusing on. So here is what the architecture can look like. And so we can see that we have these legacy systems, and then we're introducing a new system here. And so we have these different types of interfaces. And so some of these systems can have a legacy system. And so maybe there's a system of systems between these three. Now we're adding this new one. And with this new one, there's a new interface that goes between two legacy systems. And then this new system has now an interface between system one and system three. And so those are the things that then have to be played out and figure out how that's going to work. So I won't go through all of these items in this table, but just mention a few just to give you an idea between what is the difference between systems of systems and traditional systems engineering. So for traditional systems engineer, it's well-defined boundaries of the systems. There's reasonably stable operational environment. A system of system may continually have changing boundaries depending on the mission and constituent systems. The environment will be under continual change based on user needs, improved technology, and different user demands. And so if you just read down this table, you'll start to see that this is clearly a little bit more structured and defined. This is now there's more cooperation that has to exist between these things. So we're showing an example of four. And so what happens if this is 2 years out from a block upgrade and the rest of them are 4 or 5 or 10 years out? And so then they have to be thinking of what happens if this goes away for a period of time. Does this mean that this system of systems is no longer operational? Or do they have to have some type of a gap filter? And this has to be coordinated with the other players. Those just gives you an idea of how things are laid out between each of those component elements. Okay, so there's 4 types of systems, and we'll have a chart for each one of these is directed. And that means there is a central authority that's guiding all of these subsystems. And so it has another layer of top-down directed operation. And so then we gradually go down from the most directed to lower levels. And the graphic that I'll show for each of these, I think, will be helpful. A lower level of coordination is acknowledged. Then below that is collaborative. And finally, virtual, when you're just using them together and there's no necessary any formal agreement that they're keeping everything in place. And so that could be the most volatile. So we're going to have this triangle, and this diamond is going to be showing you how it goes here. For a directed system of system that's all the way over here, there's full control. The purpose is specific and dictated to this highest level. The management is centralized and authoritarian. Has a rigid and hierarchical structure, and the standards are mandated. Very clear, and this is going to be easy. Now let's start to look at it a slightly less and acknowledge that the level of control is by majority rule. And so it's not like a king that's directing things or however you want to look at it. The purpose is recognized. Everybody sees value about it. The management is top-down collaboration, emphasis on collaboration. The structure is flexible within a framework, and the standards are enforced. So that's the next level. Going down a little bit further, collaborative. The level of control is at the components. And so just going back up a few slides for a moment, all of these are independent. And so it's just a coalition of the willing that's directing things how they're going. The management is bottoms up collaboration. So if one all of a sudden has a funding hit, the whole system of system could operationally go down or be degraded. The structure is flexible and the standards are adopted. Okay, we're all kind of using the same standards here, and so we're going to go with that. There may be a little bit of deviation, and so we may have to have some applique to go from one standard to another to ensure we have connectivity between all of the elements. And finally, in virtual, there's little or none type of control there. The purpose may not be apparent to the components. The management is decentralized. The structure is dynamic and the standards are informal. So there's going to be a lot more this intermediary layer that's going to be doing this translation that's going to be required for that to work. Well, this is in our textbook, and so you can look this over, but here is just some examples of systems of systems. And so you can be thinking of an air operations center. And so maybe you have different type of aircraft. Maybe you have helicopters, unmanned vehicles, aircraft. All of these are part of the mix. And then you have different types. Some are maybe for surveillance. Some are for passengers. Some are for supply transport. All of those can be things that we see in a system of systems. So some of the challenges would be coordination among multiple systems to accomplish mission planning. And so there needs to be a strong command and control for that to happen. You can think of a ballistic missile defense system. And so one of you doing a project on missile silos, you can see how this is going to be something that you're going to have to be thinking about. A missile silo is a larger part of a larger entity. And so this example is talking about a ballistic missile rather than a cruise missile defense system. And there's a collection of sensors, battle management, interceptors to defeat incoming missiles and stuff like that. You can have other things in the science area. You can have something called the Global Earth Observing System of Systems. And so this is a multinational effort to collect and share observations of Earth. And so we can have NASA working with ESA, working with other entities, say in Japan or Canada. So those are some things where they would have to be working on. There's something that's going on with the FAA is the next generation air transportation system. I mentioned briefly this idea of unmanned vehicles. And so this is something that's being laid out as well as new ways to improve safety, efficiency, and resiliency. So that's an example of a system of systems. And so thus you can see a lot of different things. And finally, the last one I'll mention is the International Space Station, where it's a multinational effort. All kinds of astronauts from different nations are combined to that. Each one is contributing equipment, resources, and all of that has to take place in a coordinated fashion. All right, well, just finishing up on a few final slides. And so what are some of the attributes of a system of systems? Here's a reference that talks about 5 initial system of system attributes. There needs to be operational independence of component systems. And so each one has to operate on its own, first of all. There needs to be management interdependence. So interdependence is the key word. And so they're working collaboratively with one another, with the components. There can be a geographical distribution. Not all of these are going to be in the same location. There is an emergent behavior. What does that mean? Is you put these multiple elements together, the sum is more than each of the parts. And so you've created a separate entity that has additional capability. There can be evolutionary development. You figure things out and you says, well, this works. Well, now we can try this. We can exploit more of the resources that we're taking in common and actually create an even greater capability. So what are some of the challenges that come up for system of system engineering? First of all, is who is in charge? A lot of the components, they would like to be the one who's dictating. And so if it's not a top-down directed, this is the thing that you're going to continue to have to be working with each of the elements. What about the interfaces and how are you going to manage upgrades? I mentioned an example. One of them goes down into a maintenance cycle before the other ones are thinking that they would be going into that mode. And so how are you going to be dealing with that? And finally, interoperability. You constantly want to make sure that you're using an agreed upon way of going from one entity to another as you're sharing resources and keeping things functional. So just to finish up, in this short chapter, we talked about systems of systems engineering. We talked about the differences between systems of systems and traditional system engineering. We talked about the 4 different types of systems, the attributes of what are part of systems, and finally, what are the challenges to systems of systems engineering. Any comments or questions on what we covered there? Why don't you just give me a thumbs up if you're tracking with that, just so I get some positive feedback before I move on. Okay, good. Thank you. So on Tuesday, we began to introduce this whole idea of how we go about using a parametric diagram. And so I'm going to introduce something that I'm going to play a video that goes into this, and then I'll come back to what I'm going to show. So first of all, I'll just give you a little of a precursor. And so I call this multiple things, Cameo Systems Modeler. It's also called Magic Systems of System Architect. And so I may call it Systems Architect. But this is an example of how you can be doing trades. And so I'm going to be exploring an example when I'm looking at how different configurations for a CubeSat. But for this example, and I'm going to play this video in a minute, is going to be looking at a car. And so here we can be thinking about two possibilities for an engine. One that is weighs 700 pounds, another one that weighs 1,000 pounds. And so here, this is a block definition diagram. So we can see a relationship between a block definition diagram, an internal block diagram, and parametrics. Mostly, I'm just going to be focusing on a block definition diagram and a parametric diagram. And so this gives us a couple things. So thus we see that we can be either choosing one or the other. So we have this open triangle here for this. So there's two possible ways. And so we have a generalization is being laid out there. So that's for the engine, and for the body, we also have something that's laid out here. So that's the block definition diagram. And now we have this parametric diagram where we're going to be exploring the first constraint is the total mass has to be less than the mass limit. And the other thing is the total mass has to be the mass of the engine plus the body combined, and that has to stay below this total mass. And we have this opportunity to actually change things out. And so that's just a little bit of a heads up of what we're going to be talking about there. I'm going to show you something like that, but for a CubeSat. And so let me just first of all go to the block definition diagram. So I have a CubeSat, and then I have two more specific examples here where I'm talking about training how much batteries. And so we have the batteries for this CubeSat 1. That's a certain type of battery state. Maybe it has 2 batteries. And so here, say it has 3 batteries. And so maybe we could pretend like it's a satellite, but just pretend like we're dealing with Tesla. And so we can have so many kilowatt hours here versus a little bit more, say 1.5 times the kilowatt hours that would be part of that. Well, for visual paradigms, this is how I was having to do some of the things I was trying to do. And so I have like constraints listed over here. And then I have things that are subservient to that. So here I'm talking about the CubeSat weight. The things that would be contributing to that are the batteries, the structure, the CubeSat size. And so if it's a 1U, a 2U, a 3U, and the solar panels, how many solar panels are going to be there. And then what I did is I created a parametric diagram over here that's trying to look at some of these things. And so with visual paradigms, with a level of what we have with our tools, we're not going to actually do some executable things with this, but this is a little bit more advanced than what we talked about on Tuesday. And so let me go over and play a video. It's about a 10-minute video I'm going to show that is going to be based on what I did with the Magic Systems Architect or Cameo Systems Modeler, whichever one you might want to think of the naming convention for that. Okay, I'm going to go back to the beginning of this, and then we'll go in and play this.
Hello, in this video, we will do introduction to parametric diagram with instance modeling and simulation. We will show.
Okay, so we're going to be having a parametric diagram, and it's also something called this other thing that unfortunately this isn't something that we can be doing in visual paradigms, but there's something called instance modeling. And that's what we're going to be seeing, where we can have a table like this. So just wanted to give a context there. And we'll be playing this. I'm going to introduce this, and then we'll continue to do some of this on Thursdays for the next couple of weeks.
How to use instance tables and manage instances with variance modeling and instance configurations for the system alternative variants. So we'll start from this block diagram. We see a very simple model here. The vehicle has total mass, mass limit, engine as a part, and body as a part.
So here we're seeing three blocks, the vehicle, the engine, and the body, and there's parts. And so you by now probably have some familiarity is when you create some element and associate it with a block, it's going to start to show up here. And so these are the things that are put into these blocks so far.
Engine has mass and body has mass. Now, if we want to create a parametric diagram here inside of the vehicle, we can do it by right-clicking and creating parametric diagram. We can also.
Okay, this is not how we do it in visual paradigms, but I'm just going to go play this out so you can get a familiar with how you can do it with another tool.
So use equation wizard. So right click on block vehicle, click on the tools, and then parametric equation wizard. And
so one of this, how this helps is you're clicking on a block, and that block you're making a parametric diagram that's related to that block. And so you're creating that association. And some of you, as you're you may have been trying to work on your parametric diagram, this may have come up that it's telling you need to do that association.
we'll type total mass equal mass 1 plus mass 2. Parse and map. Here we have constraint created, and here we have system properties. And we will map mass 1 to mass of the body, mass 2 of mass of the engine, and click OK. You get parametric diagram created.
So basically, he did a couple of associations, and then this auto-generated this parametric diagram, which is kind of cool. So just hang on here. I think this is amazing. And we'll just go beyond some of the things we can do with visual paradigms as we get this introduction to model-based system engineering, now getting into some analytics and analysis of what this all means.
Now, second part of the parametric diagram could compare the total mass to mass limit, right? So I will take this parametric diagram and will click on this equation wizard again, but now on parametric diagram, I will click it without selecting anything, because if I will select this one, I will see the equation wizard for the same constraint, but now I will click without selecting it. So I can add another one. So total mass should be less than mass limit, and parse and map. I get recognized names of the properties, and I click OK, parametric diagram updated. Now I can run this.
So just having the names, it's able to create these two constraints and then just auto make those associations and lay them out.
It doesn't matter if it will run in context or without, it always runs in context, right?
So here's another feature that I've showed in a couple of different types of SysML diagrams, and it also works for parametric, where you can actually do this run. And so let's just see what he talks about for this.
And I see the result here. So in simulation dialog, I see that the mass limit is 5,000, total mass is 3,000. This comes from the body mass and engine mass, if I will update any of them.
So what this does is it's either going to be green, greenish or reddish. So if it meets those constraints, this means this is fine. If it doesn't, it's going to change its color. That's a feature that I haven't been able to figure out how to implement that. But even without that, you can read this and see what's going on.
Parametric diagram immediately recalculates. And if the constraint is not satisfied, I see that the red color and constraint is not satisfied. Constraint is satisfied, I see green color. Now, this configuration is taking properties from the default values of the block value properties. Here we see this coming from those properties, but it's not always good. because I might have alternative configurations and I want to save them with an alternative configuration simulation results. For that, we use instance.
So this just kind of gives you a rough idea if it meets these constraints. Now we can be thinking about two type of vehicles, and he's going to create those, and then we can go either one or the other, and help us in our analysis to figure what option we're going to choose.
So I will right click on the vehicle, will click on this second button, export to new instance, and then we'll create package system model configuration, this package, and we'll create instance in that package. So I created new instance in the package. Let's see what's happening here. I have instance of this in this package of the system model with all the properties as it was at that moment. So I will go now here, and if I will simulate this instance, what will happen is that it will run this block simulation and will load the properties from that instance, whatever was saved in this model. You can also update here in the instance directly. You can update here. Let's say that I want to update engine to 7800, right? And then select the top and save as the instance. And you see that now I got engine updated, mass updated to 800. And this is not the default value of the engine, right? This is that instance, which I can always invoke by simulating this. So to work with instances, there is really convenient with the instance table because it allows to show compactly instances, plus it allows you to see what only properties you care about. So I will create instance table as a diagram in the same package. Here we see two fields, classifier and scope. I will set classifier as the vehicle. This is the block, which instance you want to show, and that's which instance we created, so the vehicle block. And then scope is the package where I have my instances. And here you can see some properties already visible, but I will go to columns and select columns and pick the properties which I want to see. So that would be mass and body mass, engine mass and body mass, okay? So now I have here configurations, mass of the engine, mass of the body, mass limit, and total mass. If I will want to create another instance, I will click here, create with parts, which will create another instance of the vehicle with all the properties inside and the parts inside. And now I could say.
So you're seeing how you're starting to get these different scenarios, vehicle and vehicle one.
That, okay, this will be like 700 here, and the body mass will be 3000. And if I will select just this line and simulate, I will run this line. If I will just simulate without selection, I will get both lines executed and value calculated, and result is compared to total mass. Okay, so that's how instance table works. So it's very convenient. There's another common situation when we have in the block diagram alternatives. For example, for the engine, we have engine 1 and engine 2, and those are variants of the engine. They inherit from the engine, right? And they redefine the property.
So you see how that's that open triangle. So now we have two engine configurations that we can be playing against each other.
The mass, right? So let's go to engine 1, go to properties in the standard mode, properties, select this property and redefine. Redefine means change in context. So I will change it for the engine 1, it will be 700 default mass, and for engine 2, it will be properties. Select redefine will be 1000 default mass. Those are alternative architectures for the engine, and you can have, separate structures for each of them, the properties, behaviors, and so on. The extra properties, for example. Now, because this property is connected in parametric diagram, when you choose one or another variant, you will get that input from this engine or this engine to the equation, right? And the same you could do for the body and any other part in the system model. So how now to pick the variant configuration? For that, instance table is actually perfect. So now to select the engine, we will select the part here in cell columns, select columns, engine. Okay, so here we have this engine. And here you see engine default one was selected. So I can go here, remove the old one, double click again, click and pick engine one here. So you immediately see 700 as the default mass for the engine. And then remove that one plus engine two. And they see 1000. And again, rerun the simulation for both variants. Now, if you want to create another variant, you can do it again with parts and with custom engine characteristics, for example, 1500, and run all of them for just one 3000, for example, 600, run level 8. And now you see that the validation, even if this one fails, does not color code. So this is the last thing I want to show in this video is actually that you need to create at least one simulation configuration diagram, which is very technical thing here. You just need to load a profile which has validation rule, which will color code those validation rules based on the constraints in the parametric diagram. So now I will execute again all that three variants. And now I will see color coded, this one is a red, and I see the constraint is mass, total mass less than mass limit is failing. So what's happening with the instance when you run the simulation from the instance is that instance is executed. Did you select all of them one by one? And it runs this classifier of that instance. So the vehicle in this case loads that structure and allows you to simulate that structure with the values coming from the instance. So it could be historical values, configuration values, including what part was selected, engine one, engine two, what values were selected, and also results of that configuration. So which could be, specific for that configuration, which as we can see here, depending on configuration, we have total mass. So it is better to keep that in instance instead of the default value of the vehicle here in the block diagram, because it is only one default value and it depends on the configuration. So that was introduction to the instance table, parametric analysis with instances, and how to create variants and to manage those variants in instance table.
Okay, I know that's a lot of information, and for me, I actually watched that a bunch of times to create this draft one of what I have right now. And I'm not going to go ahead and execute this today, but I just wanted to give you a rough sense of what's going on there. So let me pause for a second to see if there's let's do as a minimum, just do a thumbs up if you were able to track at least at a general sense of what they were doing, just trying to give you a survey perspective of some of what you can be doing with a parametric diagram. Okay, good. Wonderful. Okay, let's go back to a couple things here. So let's go back to Freudenthal, and I read a little bit about this, and I'm just going to finish giving an introduction to this. And so this is chapter 8. So the overview, a typical design effort includes the need to perform many different types of engineering analyses, such as trait studies, sensitivity analyses, and design optimization. We just saw that with the video. It may include the analysis of performance, reliability, costs, and physical properties of the system under consideration. SysML supports this type of analysis for the use of parametric models. Parametric models constrain the properties of the system, which then can be evaluated by appropriate analysis tool. And I showed you briefly a presentation that talked about connecting MATLAB with a SysML type of program. Constraints are expressed as equations with the parameters of the equations being bound to the properties of the system being analyzed. Also with the Magic System Architect or Cameo Systems Modeler, there is some things that you can actually do within the same tool if you get all the right add-ons. A parametric model which captures multiple engineering analyses such as performance, reliability, and cost can be analyzed to perform a particular design alternative, support trade-off analyses, or optimize a design based on multiple criteria. SysML introduces the constraint block to support the construction of parametric models. The constraint block is a special kind of block used to define equations so they can be reused and interconnected. Constraint blocks have two main features: a set of parameters and an expression that contain those parameters. Constraint blocks follow the patterns of definition that and use that applied to blocks and parts as described in the chapter before this, chapter 7. A use of the constraint block is called a constraint property and is analogous to a part property. The definition in the constraint blocks is represented as a block definition diagram and parametric diagram respectively. The semantics and notation of constraint blocks in the SysML hierarchy are heavily influenced by there's a reference here that's laid out. So that's just a little bit more context for you all to consider. And so where do you start? Maybe not something so complicated as this, but we can get a chance to be thinking about this a little bit more. And so I had relatively speaking, a simpler type of model. This was a relatively simple one that was just trying to show a couple of things. So why don't we just have so any questions on what I've covered so far? Okay, like I said, I saved this one for last. It does get a little bit more complicated. But you can start to be thinking about how you're going to be looking at things. And so there's a term that's used in space systems that's called SWAP, which stands for size, weight, and power. And so there's a contribution here for what is the total weight. So there's that. You have the size, and so CubeSats, they have this designation, like a 1U is like a 10 centimeter cubed. A 3U would be 10 centimeters by 10 centimeters, would be 30 centimeters long, and so it can be a little bit larger. And so that would be things to do with the size, and then we have the power. And so those would all be things that would be playing into calculating the swap. I was trying to show similar to what what we saw in that video, that you limit the max weight. You only can have so much weight. You're only going to be able to produce so much power. You're only going to be able to put on so many solar panels onto the surface for a CubeSat. These are all things that have to be thought about as you're doing your design. Okay. So let me stop sharing my screen for now. If any of you would like to share what you're doing with your project, feel free to do that. Or if you just want to have a dialogue, please let me know.
Can I show you what I did in Visual Paradigm? Because I'm not sure if it's like, I'm not sure how to connect the different things in Visual Paradigm.
Yeah, sure.
Um, Can you see that?
Yeah, I can.
Okay, yeah, I'm not sure how to like show that.
Okay, this is something I was just figuring out. So, right click on the property weight. No, I'm sorry, not right click, but get that little thing in the upper right corner right there. Yeah, click on that. Yeah, click on that one. So you want to create a new port and name it something.
Wait.
Just, okay, now which one of these things on the right would you like to connect it to?
All of them. Well, because
Okay,
they're all, yeah, like all of them will have a weight that needs to add up to a certain value.
okay. I think you created two ports. Yeah, I'm not quite sure if you still have, okay, you just have one, good. Okay, so right click on the battery one. Let's just start with that. And click on that first one. Now click in weight right there. Now that's,
Oh,
so
okay.
this is where every tool is a little bit different. And this is not the only way that you could do it, but is one of the ways that you can create that connectivity. Okay.
Okay. And then how many like different parameters do you want us to do?
I would say at least have three. Let's just think of that. And so you have like it's called, each one of these is called property. Maybe there's something um, more definitive that you might want to be including with those naming conventions, but if that's going to be up to you.
Okay. Thank you.
All right. Well, thank you, Abby, for sharing that. What I'd say is one of the things in terms of modeling, the first question you always have to ask is, what are you modeling for? What do you want to be accomplishing? And so Abby is starting to look at a couple of things. I think it was weight that you were looking at. And so what would be the contribution from the major components of her vehicle that, and then aggregate that together into a parametric way of looking at it. And so you could constrain that, say like the regulation is a vehicle can't weigh any more than 10,000 pounds, just off the top of my head, just thinking of a notional number. And so that gives you your budget, and then you can figure out how you're going to allocate that. That goes something similar to like I was talking about a CubeSat. You could say that the maximum weight might be 2 pounds or something like that. And so the power might be 5 watts. And so those are the things that you then have to figure out how you're going to allocate that across everything that you want to be accomplishing. Okay. Anyone else have something they'd like to get a chance to share?
So will we need like specific number values for each of the, like for example, each of the different weights?
Um, I would say at least having it set up so that you have more than one possibility. And so let me share my screen again. By what I mean by that. So here what I was doing is I was finding myself having to go back between block definition diagrams and the parametric. And so here I have two examples that have different battery sizes. And so then I could start, and then I have the constraints that I have laid out here that I mentioned before. And then when I go to a parametric diagram, then that's what's going on. But behind here is the number of batteries. This is where that, depending if I'm using the CubeSat 1 or CubeSat 2, that's where that would show up. Okay. Well, why don't I let you guys have a chance to be developing that? Let me just quickly go around the room. Nathaniel, any comments or questions? You have see a path forward for how you'll go about doing this?
No questions. Just need to think a little bit about what I want to show in my diagram.
Okay. Jonathan, any comments or questions or any ideas what you would like to do with your parametric diagram?
No questions. I'm just trying to work it out now.
Okay. And Kyle, any comments or questions?
Not really. It's gonna be interesting, trying to figure out all the little restrictions around making sure this thing has enough power as it makes a loop around the Earth.
Okay, well, I think that's probably a good breaking point for now. So we're getting close to finishing up the lecture material. And so I'll have a couple other things that I'll be bringing up related, but how do we can be tying this all together from a systems engineering point of view. So I hope everybody has a good rest of your day. God bless you. Take care. Bye-bye.
Thank you.